Hello students. I got a request from a few of you to help you understand the Gauss's theorem on the basis of a few solved examples. So here I am with a few simple and important examples of Gauss's theorem that will help you work out questions as well as to understand the concept of Gauss's law. Let's begin. Let us first of all state what Gauss's theorem says. It says that total flux phi associated with a closed surface is equal to 1 by epsilon 0 times total charge enclosed by the surface. Here QEN represents the total charge enclosed by the given surface. So now let us try to apply Gauss's theorem. Suppose we have a closed surface S and suppose that it encloses a charge Q. Now you can see that all the lines of force that are originating from this point charge are cutting through the surface S. So if we wish to find out the total flux associated with surface S, that flux will be equal to 1 by epsilon 0 times charge Q. Now the shape or the size of a Gaussian surface does not make any difference as long as the charge enclosed by it remains the same. So whether this be the surface or this be the surface or the surface has any other shape or size, the flux remains the same. Now, if you recall the video on Gauss's theorem that I provided, you may see in one of the applications that it can be used to find out electric flux associated with open surfaces also. Now, let us consider a circular surface at the center of which we have a charge Q. And suppose that a hemisphere is drawn with the circular surface as the base. Now, again, you can see that because the charge is exactly at the center of the sphere, center of the hemisphere. So on the lower side, the flux leaking will be equal to 1/2 of the total flux. This can be stated from symmetry because a point charge exhibits a spherical symmetry. So if we want to find out the total flux phi associated with the hemisphere, so the total flux associated with the hemisphere will be equal to 1/2 of the total flux, which is equal to Q by epsilon 0. A few other examples can also be stated. For example, if we have a cube, I'm drawing a cube and placing a charge Q exactly at the center, that is at the point of intersection of body diagonals of the cube. Suppose this charge be Q. Now because it is within the cubical surface, so the total flux associated with the cube will be equal to 1 by epsilon 0 times charge Q. This is the cube C. You can see that because the charge is exactly at the center or point of intersection of body diagonals, so equal amount of flux should leak out or should cut through each of the square surfaces of the cube. So flux associated with any one of the square surface, say S, will be equal to 1 by 6 of total flux, which is equal to 1/6 of Q by epsilon 0. A lot of other examples can also be stated. Now let us have a square surface having a side A, and exactly at a point above the point of intersection of diagonals of the square at a distance a by 2, suppose we have a charge Q. If we wish to find out the total flux passing through the square surface, we can draw a cube with the square face as one of the face of the cube. So you can see that if you complete the cube, you will again get the charge q exactly at the center of the cube. So again, the total flux associated with surface S can be written as 1/6 of q by epsilon 0. Another example we can use is, suppose we have a pyramid, an equilateral pyramid, and suppose that we have a charge q placed exactly at the centroid of the equilateral triangular base of the prism. Now obviously no flux is associated with the base of the prism because the charge lies on that base. Also from symmetry we can see that equal flux is associated with the three faces of the prism. And we can also say from symmetry that total amount of flux associated with the three faces is equal to 1/2 of the total flux. Total flux associated with the charge that is escaping on all sides, all directions of the charge. So total flux streaming through the three faces taken together will be equal to 1/2 of the total flux, that is 1/2 of q by epsilon 0. And because equal amount of flux is escaping through each of these triangular faces excluding the base, so the total flux associated with each of the triangular surface will be equal to 1/3 of this value, that is 1/6 of q by epsilon 0.